Look up at the night sky. What do you see? You might see the moon, a familiar silent neighbor. You might see the faint glow of planets like Mars or Venus. And you will definitely see stars. Billions of them. Each star is a distant sun, and many of them likely have planets of their own. For all of human history, we have looked up and wondered. We have dreamed of visiting these other worlds. We have imagined what it would be like to walk on another planet, to see a different sun rise in an alien sky. This dream is a powerful one. It is part of what makes us human. This dream is no longer just a story. We have sent robots to Mars. We have walked on the moon. When we think about leaving Earth, our minds naturally go to planets. Mars is the most talked about destination. It has a certain romance to it, the red planet of so many stories. But living on Mars would be incredibly difficult. The atmosphere is thin, almost a vacuum, and it is unbreathable. The gravity is only about 1/3 of Earth's, which could have serious long-term effects on our bodies. And Mars is cold, dangerously cold. It is a desert world, bombarded by radiation from the sun. We would have to live in sealed bases, likely underground, always separated from the hostile environment outside. What if there was another way? What if, instead of trying to change a hostile planet to suit us, we built our own world from scratch? A world designed perfectly for human life. A place where we could control the weather, the length of the day, and even gravity itself. This isn't science fiction. It is a serious idea proposed by a brilliant physicist decades ago. The story of the O'Neill cylinder does not begin in a top-secret government laboratory or a futuristic corporation. It begins in a university classroom. It starts with a physicist named Gerard K. O'Neill. He was a professor at Princeton University in the late 1960s. O'Neill was a high-energy physicist, working with particle accelerators. In 1969, the world was captivated by the Apollo missions. Humans had just walked on the moon. People were asking big questions about our future. Could we live in space? Should we? O'Neill was asking these questions too, but he was looking for practical answers. So he decided to turn this question into a challenge for his students. He created a special seminar for his first-year physics class. The question he posed was simple but enormous in its scope. Is a planetary surface the right place for an expanding technological civilization? He encouraged his students to think freely, to use the laws of physics as their guide, but to let their imaginations run wild. He wanted them to calculate, to engineer, and to design a real workable home for people in space, starting from first principles. Gerard O'Neill's students really took his challenge to heart. So, they started working through the problem step by step. First up was the location. They eventually identified these specific points in space, called Lagrange points, where the gravity of the Earth and Moon balances out perfectly, creating stable spots for a habitat. They turned to the Moon, which has a much shallower gravity well, and to the asteroids, which are actually rich in metals, carbon, and water. After crunching the numbers, they realized that mining these celestial bodies would be far more efficient. The answer was this large, sealed, and rotating structure. The rotation was really the key. By spinning the habitat, they could use centrifugal force to simulate gravity. That way people could live, work, and grow up with the familiar feeling of weight, which would protect their bodies from the negative health effects of zero gravity. The students, with O'Neill guiding them, worked out all the details. They even calculated the ideal size and rotation speed to produce Earth-normal gravity without causing motion sickness. They designed systems to provide air, water, and food, and they imagined how sunlight could be brought inside using mirrors, creating a normal day-night cycle. Slowly, a whole picture started to form. It wasn't just a small, cramped outpost. It was a vast, self-sustaining world. O'Neill was so impressed and inspired by his students' work that he dedicated himself to refining and promoting the idea. What started as a classroom project had now grown into this revolutionary vision for colonizing space. As Gerard O'Neill developed the concept even further, he laid out a whole series of designs, each one more ambitious than the last. He called them islands. The first one, Island 1, was a relatively small sphere, about 500 meters in diameter. It would rotate to provide gravity, and could actually house around 10,000 people. O'Neill saw this as a construction base, a kind of starting point. Its residents would be the pioneers, building larger habitats and developing the industries needed to mine the moon and asteroids. It was a practical first step, a proof of concept to show that living in a manufactured world in space could really work. The next step was Island 2. This was a bigger design, sometimes imagined as a sphere, sometimes as a torus, which is like a donut shape. It would be a more permanent settlement, basically a small city in space, able to house over 100,000 people. There would be more space for agriculture and recreation, making it a much more comfortable and Earth-like environment for everyone living there. These weren't just functional stations. They were meant to be beautiful places to live. But the ultimate vision was Island 3. This is the design that became really famous as the O'Neill cylinder. It was a truly massive structure, a pair of counter-rotating cylinders, each about 32 kilometers long and 6.4 kilometers in diameter. The inside surface of each cylinder would provide over 1,300 square kilometers of land area. That's enough space for millions of people to live in a landscape of forests, mountains, rivers, and towns. O'Neill's vision was incredibly detailed. He described how the land inside the cylinder would be divided into 6 long strips, 3 valley areas for living, and 3 window areas to let in sunlight. The design of an O'Neill cylinder is, honestly, both simple and breathtakingly ambitious. At its core, the concept is a pair of enormous, hollow cylinders. Each cylinder in the pair would be truly vast, measuring around 32 kilometers in length and about 6.4 kilometers in diameter. Just to put that into perspective, you could actually lay the island of Manhattan inside one of these cylinders and still have room to spare. The 2 cylinders would be placed side by side, connected at their ends by a sturdy framework. They're designed to rotate in opposite directions, which is a clever bit of engineering. By having 2 cylinders spinning in opposite directions, their gyroscopic effects cancel each other out. The interior surface of each cylinder is where people would actually live. This vast curved landscape would provide an enormous amount of land area, about 1,300 square kilometers in each cylinder. For a cylinder with a diameter of 6.4 kilometers, it would need to complete a full rotation roughly every 2 minutes. This gentle spin would create a centrifugal force that pushes everything inside outwards, towards the inner surface of the cylinder. For a person standing on that surface, this force would feel exactly like gravity. It would hold them firmly to the ground, giving them a normal sense of weight. This simulated gravity would make almost every aspect of life feel normal. Water would flow downhill into rivers and lakes. Rain would fall from the sky towards the ground. Plants would grow upwards, and buildings would stand securely on their foundations. A world needs a sun. An O'Neill cylinder, floating in the darkness of space, creates its own day and night in a remarkably ingenious way. The system is designed to capture, control, and distribute natural sunlight throughout the vast interior of the cylinder, mimicking the patterns we experience on Earth. By slowly changing the angle of the hinged mirrors, the inhabitants can make the sun appear to move across their sky. They could make it rise in the morning, travel overhead during the day, and set in the evening, just as it does on Earth. By making subtle adjustments to the mirrors over the course of a year, the inhabitants could create seasons. They could simulate the long, bright days of summer and the shorter, cooler days of winter. Once we have the materials, we face the next monumental challenge: construction. How do you build a structure that is 32 kilometers long in the middle of space? In space, everything is floating in a vacuum. The environment is one of extreme temperatures, with scorching heat in direct sunlight and deep cold in the shadows. The construction process would have to be highly automated. Instead, we would rely on an army of advanced robots. They would be responsible for catching the raw materials launched from the moon, processing them in orbiting factories, and fabricating the components of the cylinder. The process would likely happen in stages, starting with a basic frame and gradually adding the hull, the internal structures, and the complex life support and lighting systems. It would be a slow, methodical process, taking decades to complete. Once the main structure is sealed, the next phase of construction begins, building the world inside. Only when the structure is fully sealed, pressurized with a breathable atmosphere, and has a stable, Earth-like gravity from its spin, can the final, most delicate work begin. This is the introduction of water, plants, and animals. The slow, careful process of turning a giant machine into a living, breathing world for its future inhabitants. An O'Neill cylinder is designed to be a self-sufficient world, a closed ecological system. This means it must provide everything its inhabitants need to live: air, water, and food. The atmosphere would be created and maintained at a pressure and composition similar to Earth's, rich in oxygen and nitrogen. The climate inside the cylinder would be entirely under human control. Without the unpredictable weather patterns of a planet, the temperature and humidity could be kept at comfortable levels year-round. The vast green landscapes, the forests, parks, and farmlands, would play a crucial role, absorbing carbon dioxide and producing oxygen through photosynthesis, just as they do on Earth. Water management is another critical system. All the water for the habitats, rivers, lakes, agriculture, and population would have to be brought in from asteroids or comets. Once inside, every drop would need to be continuously collected, purified, and reused. Perhaps the greatest uncertainty is the stability of the ecosystem itself. We would be creating a completely artificial biosphere from scratch. This vision of a world in a bottle is what makes the O'Neill cylinder so compelling. It is not just a machine for living in, it is a living world in its own right. Even if we can solve the technical challenges of materials, construction, and life support, we're still left with two final formidable hurdles: cost and risk. The price tag for building the first O'Neill cylinder would be, well, staggering. It would require a level of global cooperation and investment that we've honestly never seen before. Proponents of the idea argue that the initial investment, while huge, would eventually pay for itself. The habitat could become a hub for new industries, like zero-gravity manufacturing, asteroid mining, and the construction of solar power satellites. However, this is a long-term vision. Getting through the initial decades of massive spending before any return on investment is seen would require extraordinary political will and a shared global commitment to a future in space. Beyond the financial cost, there are also immense risks. A habitat housing millions of people is a single point of failure. What if there is a catastrophic structural flaw that was missed during construction? A major breach of the hull could lead to explosive decompression, an unsurvivable event for anyone exposed. There are also social and psychological risks to consider. How would a society function when it is physically isolated from its home planet? The creation of an O'Neill cylinder is not just an engineering project, it is a profound social experiment. The potential rewards are a new frontier for humanity, but the stakes, financial, technical, and human, are incredibly high, demanding careful and deliberate progress. When we look at the colossal vision of an O'Neill cylinder, it can feel like pure science fiction. However, if we break the problem down into smaller pieces, we can see that we've already taken the first steps. We have a permanent human presence in space aboard the International Space Station. For over 2 decades, astronauts have been living and working in orbit, teaching us invaluable lessons about long-duration spaceflight. We also have growing experience with robotics in space. We've sent sophisticated rovers to Mars that operate semi-autonomously for years. In terms of materials, our understanding of space resources is growing every day. Recent missions have also confirmed the presence of water ice in permanently shadowed craters at the Moon's poles. This is a real game changer. While we have a solid foundation, there are still several key technologies that need to advance dramatically before we can seriously consider building a space city. The most significant leap required is in space-based manufacturing and resource utilization. We need to go from simply analyzing moon rocks to being able to mine, process, and refine them on an industrial scale. Another critical area is closed-loop life support systems. To support a city of thousands, let alone millions, we need to develop biological and mechanical systems that can recycle air, water, and waste with near 100% efficiency. We will also need a revolution in our ability to generate and handle power in space. An O'Neill cylinder and its associated industries would require vast amounts of energy. The journey to an O'Neill cylinder, well, it won't happen in one giant leap. The logical roadmap honestly begins with a return to the Moon, but this time, the goal is to stay. The next step in the roadmap would be to build the infrastructure in space needed to support construction. That means building an electromagnetic mass driver on the moon to launch processed materials into a stable orbit. With the supply chain established, we could finally begin construction on the first true space settlement. This wouldn't be the giant Island 3, but Gerard O'Neill's more modest starting point, Island 1. Finally, once Island 1 is built and proven to be a stable and successful home, the real work can begin. With lessons learned from building and living in the first settlement, we could move on to building an Island 2, and eventually, the magnificent Island 3 O'Neill cylinder. We stand at a remarkable moment in the story of our species. For the first time, we have the knowledge and the emerging technology to seriously consider a future beyond our home planet. The O'Neill cylinder is more than just an engineering blueprint. It is a profound statement about human potential. These spinning cylinders offer a solution to the fundamental problems of space settlement. They provide Earth-like gravity through rotation, a controlled climate through ingenious engineering, and a safe harbor from the harsh realities of the cosmos. This vision places humanity at a crossroads. One path leads us to continue as we are, a species tied to a single fragile planet, facing the growing pressures of resource depletion and environmental change. Another path leads us to the surfaces of other planets, a future of survival and adaptation against the odds. But the O'Neill cylinder points to a third way. It is a path of creation, of proactive design, where we take the raw materials of the solar system and shape them into new homes perfectly suited for us. It is a future where we become not just explorers of the universe, but architects of new worlds within it. The question is not whether we can build an O'Neill cylinder today, but whether we believe in a future where such things are possible, and whether we are willing to take the first difficult steps in that direction. The ultimate promise of the O'Neill cylinder revolution is not just about technology or economics, it is about the future of life itself. By learning to build our own habitats, we unshackle humanity from the fate of a single planet. Each habitat could develop its own unique culture, its own form of government, its own art, and its own way of life. It would be a new renaissance, a Cambrian explosion of human societies. The stars are calling. For centuries we have looked up and dreamed. Now we're beginning to understand how we might answer that call. The O'Neill cylinder is one possible answer, a magnificent vision of a future where humanity is not confined to one small corner of the universe. It is a future where our descendants might live in beautiful sunlit worlds of their own making, looking out at the star-dusted darkness with the same sense of wonder we feel today, but with the knowledge that they are citizens of a truly solar civilization. The journey will be long and arduous, but the destination is nothing less than a new chapter for humanity.